this paper, which is not yet a published paper, I would say. But since this paper happens to be the most relevant paper to my research right now, and the paper answers a lot of questions that I had, which is why I chose to present this paper, despite the fact that it has not been accepted at any conference yet. So yeah, I'll start my presentation now. So the title of the paper is NerfDiff Single Image. So the title of the paper is NerfDiff Single Image View Synthesis with Nerf-Guided Distillation from 3D-Aware Diffusion. The contributions of the paper are as follows. They developed a novel framework for view synthesis, which they call NerfDiff, which jointly learns an image condition NerF and a conditional diffusion model, and at test time fine-tunes the learned NerF using a multi-view consistent diffusion process. And then they introduce an efficient image condition NerF representation based on camera line triplanes, which is the core component enabling efficient rendering and fine-tuning from the conditional diffusion model. And then they propose a 3D-aware conditional diffusion model, which integrates volume rendering into 3D diffusion model, facilitating generalization to novel views. So before discussing the methods in detail, I would first go over the background of NerF and diffusion models, which the proposed architecture heavily relies on. So to start off with NerF. So to explain the problem setting, let's say we have multiple images of a scene from different angles, and we want to model a 3D representation of that scene using those images from multiple angles. So the way we do this with NerF is we define a world coordinate system, 3D world coordinate system, and then for every image we have representing the scene, we have the camera pose of that particular image, which we use to ascertain the position of the camera in the 3D world coordinate system when it took a particular image. So in the illustration you can see, let's say this box here, this cuboid here represents a world coordinate system in 3D. And let's say we have these two images of the scene, and these are the viewing points. With camera pose, we can, with the camera pose of each of these frames, we can determine the position of the camera with respect to the world coordinate system when it took the photos. So the goal of modeling the scene in 3D in this coordinate system is so that we can look at this scene from angles that are different to basically from any angle, to be able to look at this scene from any angle and generate an image from that angle, which may not be present in the training images. So so to get into the setting, we have an image, a training image, and we assume rays going into the 3D world coordinate system through every pixel of that frame, as you can see here. And to model a particular ray, we need this viewing direction parameter, which is basically just the angle of the camera, or angle of the ray. And what we then do is along a particular ray of a particular frame, we sample 3D coordinates along 3D points along the ray, and we query them. And when we say we query a particular point, what we do is we take the 3D coordinate values of that particular point and we feed it into an MLP along with the viewing direction of that particular ray, and we get as an output the RGB, basically the color pixel value of that particular of that particular 3D point and a volume density. So what this volume density represents is, of course, color. We all know the 3 RGB values of that 3D coordinate system. The color is basically, what the color is at that point of the scene. And the volume density represents the sort of objectness of at the 3D coordinate point. Basically, what it means is with high volume density at a particular 3D coordinate, it would mean that there is a solid object and the light cannot pass through it. So the lower, for like empty positions in the 3D coordinate systems where there's nothing but air, the output volume density would be expected to be very low. And where there is an object, it would be high. So when we have the color value and the volume density of particular 3D points, and when we have this for multiple points along array, we can use this particular formula to this integration for a particular array for every coordinate that we queried along the array. We can integrate over all those points and get the color that we are going to see in that particular pixel. So we do, to form an image, we do this for maybe every pixel. We sample multiple points along the array, 3D coordinates, and we get these two values, the color and the volume density. We integrate over all those points and we get the color value, and this is how we form an entire image. And these are the, so let's say, of course, I already explained what a world coordinate system is, and then we can use the extrinsic matrix, camera extrinsic parameters, to transform the points in that world coordinate to camera coordinates, which is basically a representation where the camera is at the origin and we define the 3 axes with respect to the camera, the XYZ. And then when we have the camera, once we have the values in camera coordinate system, we can use the intrinsic matrix to transform points in the camera coordinate system to image coordinates, which would be a 2D representation. Image coordinate basically just means the image we are going to see. So it's just 2D, just XY. So now coming to pixel NeRF. So for original NeRF, we need tens to hundreds of multi-view images of a scene from different points. But pixel NeRF just models this 3D scene using only a single image of the scene, no multi-view inputs. So in case of original NeRF, the formulation becomes like this. This I would be one of the images that you sample from the data, and then the rays would be the corresponding rays for that particular image. And then this would be the color value of that particular ray. And then, of course, we have the ground truth value, and you simply calculate the MSE loss, and you do it for the entire training set, and yeah, you optimize for this loss. But in pixel NeRF, we need 2 images. So let's say for a particular scene, we need 2 images. And as you can see in the formulation, besides the theta parameter, which is the MLP in case of NeRF that we discussed, this one. So besides, in pixel NeRF, besides that particular MLP, we also have these new W parameter. And then again, you get color values, and then you find the MSE loss over it. And for pixel NeRF, despite the fact that it's at test time, it is expected to use a single image of a scene. During training, we need 2 images because we need to form, for the new views, we need a ground truth. So we need 2 images of a scene. So the way pixel NeRF works is pixel NeRF first extracts a feature volume, the W parameter that I specified, from an input image of a scene, and they use this an encoder to get this feature volume W, which is a learnable image encoder. Then for any 3D point in the input camera space, its corresponding image features are obtained by projecting X onto the image plane as this P of X between -1 to 1 with known intrinsic matrix, and then bilinearly interpolating the feature volume as this. So what this essentially means is that you take an input image of a scene, you get this feature volume representation through an encoder, and then you transform it to the camera coordinate system, and then you project this points X coordinates for array onto the image plane, which is just the two-dimensional XY. It's basically just the image you see. And then you, for a particular array, the X coordinates that you sample, of course, you project them onto that particular pixel that it would belong to in the image plane, and you get the feature volume for that particular X coordinate by bilinearly interpolating this feature volume that we got earlier for the whole image. And then, yeah, this is what the loss formulation looks like for pixel NeRF, we already saw. So this is where this W parameter comes from. So in single image input NeRFs like pixel NeRF, we say the problem is under constrained. Basically because, let's say, in regular NeRF, since we have multi-view images for arrays going through from multiple directions, the X coordinates that we sample might come from multiple rays from multiple different directions, and this sort of introduces enforces of sorts a 3D structural requirement, so that for NeRF that uses multi-view images, the structures that are formed in the representation are multi-view consistent. But when you use just a single image as an input, what happens is that the NeRF representation overfits to a particular input view, as you can see here. So when you view it from the input view direction, it looks just like the image that you receive for that input view. But whenever you go to a new view that does not exist in the input view, this sort of breaks apart, the shape doesn't form. So that's the problem when you have a single image input NeRF. And another issues with NeRFs in general, not just single input NeRF, is when you try to generate views from directions that are very different to the views that were present in the training sets. The rendered view comes out to be very blurry. So these are the problems that this paper aims to solve. In case of, so one solution for this blurry outputs in uncertain regions would be, let's say, to use diffusion models. I'll get into diffusion models, but diffusion models basically, since they work by denoising blurry images, one would expect that they would be good at getting a sharper output out of these blurry rendered views. So, but there are problems associated with that as well, which I'll discuss later. So to get into that next, I'll go very briefly over what diffusion models are. So in the forward process during training time, let's say what happens is you take an image and then we sequentially add noise to it in multiple steps, in T number of steps, to the point it becomes completely very close to what a Gaussian noise would look like. And at every step, the noise that to be added is sampled from a Gaussian distribution, and this noise added is relatively small. And then you save these sort of degraded images at every step and their corresponding time step. And then in the backward process, what you're supposed to do is essentially go do this process in backwards. So take a noisier image and generate what the image looked like before a slight amount of noise was added. So to do this denoising, typically we use a denoising unit where, so for this entire process to like this entire series of noising, to reverse that, we use the same model at every single step. So the way the model knows at what stage of degradation the input image is, it uses time embeddings for that particular image. And so essentially what happens is like this: you put a noisier image and some transformed version of that embedding of that particular time step, and you get slightly denoised image, and you do this over and over again until you get a very sharp image. So this is how a denoising diffusion model learns the data distribution. So during test time, what you would like, what happens is that it samples a Gaussian noise, and from that, it iteratively repeats this step until it gets a very sharp image of that represents, that would be very close to what the input images in the, basically images in the training set looks like. But this is like the unconditional form of diffusion, so it's completely normal, completely random. You have no control over the sharp image that's generated from pure noise. So then we have conditional diffusion models, where you try to sort of manipulate what type of output comes out of the Gaussian noise. So what happens is that now you make the denoising process dependent on additional conditions, which might be text embeddings or image embeddings, etc., to manipulate the final output in a desired manner. So the difference between the last one and this one is merely this text embedding or an image embedding, which is an extra condition that you add to the model, and then you manipulate the output. So one example of a conditional diffusion model would be stable diffusion, where besides the Gaussian noise, you insert some text, and then that text is what guides the final output, and that text is how you manipulate the final image. So let's say you want to do novel view synthesis, or like model this 3D scene and generate new views from different angles, purely using a diffusion model, no NeRF, no geometry assumption, nothing. One way to do that, one naive way to do that, would be to sort of condition that image on a real image of a particular scene, and maybe the camera parameters too. And then for the view you want to generate, you input the camera pose of the view you want to generate, and then that sort of guides the view for the diffusion model. But since this entire process has no physical guidance, or like any 3D guidance, this is entirely a 2D process. You just put one 2D image, and then it uses that 2D image to generate more 2D images from noise. Since it's like that, basically the synthesized novel views of conditional diffusion models in the sampling stage tend to be multi-view and consistent, meaning the new views you generate might not have exactly the same objects that are there in the input, or the appearance might be different, the number of objects might be different. Yeah, basically that, like there is no multi-view consistency. So this is the proposed architecture. We finally come at the proposed architecture of this paper. So to take an overall look, the way it sort of combines the best part of NeRFs and diffusion models to do novel view synthesis. So what we have is, there's an input view, let's say, of a particular scene. You pass it through a unit encoder, and then you get these feature representations, and in the end you get a regular NeRF output. And then on top of the NeRF output, which might be blurry, you feed that NeRF output as the conditioning to a diffusion model, and hopefully you get a better denoised output, a more sharper image. So yeah, the proposed this architecture, the name that NerfDiff, this consists of an improved single image nerf based on local triplanes and a 3D aware CDM built on top of the single image nerf outputs. So like I said, like there are two components, the nerf component and the diffusion component. The way we optimize this is using the loss for taking a loss over both the nerf part and the diffusion model part. But at test time, they adopt a second stage fine-tuning, which is to mitigate the inconsistency brought by diffusion models. And then they present NeRF-guided distillation NGD algorithm to improve the fine-tuning performance. So this fine-tuning performance happens only during test time. So I'll now go over all of these components in detail. So most existing single view models like Pixel NeRF query the extracted features by image plane projection, like I explained earlier. They squash, basically, they sample 3D coordinates and then it's projected onto the 2D image space and then they query them. And since a long array, multiple 3D coordinates are projected onto the same 2D position in the image plane, there is no way to differentiate between different x coordinates along the array. So the depth information is lost. It's squashed into just a point in the image plane. So they say the 3D supervision is sort of lost in that case. So what they usually, the single image NeRF, how they overcome this issue is, besides just the volume feature that they obtain from the image plane, they also input the x coordinate into the MLP along with those extracted features, and the x coordinates have to be sort of embedded into some sinusoidal functions, so that they are of high frequency. And then, but like they claim that this embedding that needs to be done to be able to individually identify these x coordinates along a particular array, this embedding is inefficient. It needs a very deep multi-layer perceptron, and this essentially slows down the rendering process. So which is why they come up with this local triplane setup. I'll get into that too. So what happens in the local triplane setup is it essentially looks like this. You have input view, you pass it through the UNet encoder, and then you obtain these volume features, and then you reshape it to this triplane, which is quite simply you can say is it's the camera coordinate system of sorts. So since we no longer have multi-view images in this, we only have a single view image. We no longer need the world coordinate system. We can just do with the camera coordinate system of that particular image view. So we just map these extracted features to this triplane setting. And the way we calculate this is shown here. So each 3D point receives a unique feature vector by bilinear interpolation within the three planes, the XY, the XZ, and YZ. And so each of these inputs are calculated like this. The PX part is merely the 2D projection onto the image plane, and the remaining Z part, which represents the depth information of the 3D coordinate system, is calculated like this, as shown, where Tn and this Tf are the near and far bounds of the input camera. So because we still maintain the Z coordinate information in this triplane setup, instead of using just the projected version of the x coordinates, we no longer need the positional embeddings of those sinusoidal positional embeddings to identify these x coordinates individually. So they say this is much more efficient and it's much more faster, and it preserves the 3D supervision. And yeah, we no longer need to assume the world or global coordinate system and global camera poses. And the next part is, of course, we have this NeRF part figured out. So for the next part is this diffusion model part. So conditional diffusion model solves the uncertainty issue, but they say compromises the multi-view consistency. To synthesize multi-view consistent and high-quality results, the authors propose a novel fine-tuning strategy at test time to distill the CDM's knowledge. The reason they do this fine-tuning step at test time is because essentially this CDM part is introduced to deal with blurry regions that occur when the rendering view is very different to the input viewing angles. So when these blurry regions would occur, it's normal that we probably did not have an input image that's close to that rendered view, basically. So which is why this blurred rendering is happening. So this which is why this fine-tuning NGD step is done only at during testing, not during training. So the way this happens is that given an input view of an unseen scene, generate multiple virtual views with the single image NeRF and the 3D aware CDM. Then the triplane that's in the NeRF is then fine-tuned, and the MLP parameter as well is fine-tuned. And then, yeah, basically the W here becomes a learnable parameter. So in this CDM, the way 3D consistency is incorporated into the multi-view diffusion is by trying to sort of model this new joint distribution, where this ZT represents the intermediate denoised image, and this is, of course, the prediction from the NeRF part, and basically to model the noise and the prediction from the NeRF part onto the very first input image that was fed into the NeRF, the original input image. So that's how they plan to incorporate 3D consistency. And basically this whole setup boils down to minimizing the MSE loss between the denoised images IT and the NeRF rendering, this I theta W, across all virtual views. So and then in this equation you see this new parameter pi, which is just the prior distribution on the relative camera poses to the input, and this parameter is just the corresponding images at that relative camera pi, again to summarize this whole fine-tuning process. What happens is, let's say we put an input view and the NeRF creates an image, and then using that NeRF output as a conditioning for the diffusion model, conditional diffusion model, we sample multiple camera poses which are within this pi. So for each of those camera poses, multiple views are generated for the entire scene, and then each of these scenes is again fed into this CDM part for the reconstruction loss. But since this can become very heavy, and this is done at every denoising step, by the way, so this can get very heavy, which is why they choose to do it in batches, like some small number of rays across all the images that have been generated during test time. And yeah, and then they optimize for this loss function. And now for the experiment results portion, they tested on 3 different data sets. And here are the results. They compare with some previous methods, and they basically are best at pretty much every single one of these metrics across all data sets, except for maybe in this case. So as you can see, they have 2 variations here, NerfDiff B and NerfDiff L. NerfDiff B is the baseline, which is just 400 million parameters. And NerfDiff L is a more expanded version, a more heavier version of their model, which is 1 billion parameters. And so another problem with these diffusion-based rendering view synthesis that existed before, or like a problem with diffusion in general, is that it tends to be very slow because of so many denoising steps during test time. So FPS becomes a problem. But as you can see, like for this model, the FPS is actually pretty good. Like during rendering time, I think it's approximately 30 FPS or around that. The way they achieve this is one of the ways they achieve this is because of that triplane system, where they don't have to do position embedding, and it's a lot faster. And here are the qualitative results on the Clever 3D dataset. This is the result of their ablation study. So yeah, this is the result from Vision&Learning, and this is their method without this, basically without the diffusion model part, with just the pure NeRF. And as you can see, as we generate views from changing angles, it tends to get blurry, and there's more uncertainty to it. And then when conditional diffusion model is introduced, by conditioning on these blurry inputs without the fine-tuning step, so the views that are generated is, as expected, is not consistent, it's multi-view inconsistent basically. So what happens is that as the angle changes, as you can see, the objects change, the appearance of the object change, the color of the object change, stuff like that happens. Basically, it's far too random, even though overall it looks like the image is generated from the training set. But yeah, of course, it's a lot more sharper than using just pure NeRF. And with the fine-tuning step included at test time, they have these perfect rendering views. So that's it from me. Thank you for listening.